guys, good morning, afternoon, evening. So welcome back to a pre-recorded class for tutorial 14, Stokes Theorem, our last tutorial for engineering maths 1, okay, or for the semester. So there are 9 questions and we're gonna go through each of the questions very briefly. Alright, so let's start with question 1. So suppose we have f, okay, which is basically negative y, x, z, so it's a vector, right? It's a vector anyway, right? And it's basically part of a sphere, okay? Below the plane, z equals to 4, oriented with an outward pointing normal. So compute the flux integral using the Stokes theorem. Okay, how do we do this? First of all, we sketch the surface, right? And the thing is, it's below the plane z equals to 4. Okay, so below the plane z equals to 4, meaning to say that at z equals to 4, right, we're chopping off the spear. Alright, you imagine you take off like a big knife and you chop off an onion exactly at that position, z equals to 4. So you basically get a hemisphere, right? You get this nice looking hemisphere. Alright, and this hemisphere, as it goes down, okay, um, it says about an outward pointing normal. So the normal at 500 is I. Okay, so what does it mean? It means to say that basically the normal is going out. Okay, this is supposed to be going outwards, not inwards here. I think I made a mistake. It's supposed to not be inwards. It's actually outwards. Okay. Let me write it in color. Okay, so it's supposed to be outwards. Alright. Because at 500, that means when the x is 5, okay, the normal vector here will be pointing this way. So therefore, your outward normal vector will be going this way. Clear? From the surface is going downwards. Okay, so if it's going downwards, that means your circular surface at z equals to 4 is going at a clockwise direction, right? That's why your vector is going normal. How do we know this? Because if you use your right hand rule, okay, if you guys remember using your right hand rule, so imagine this is your right hand, okay, you're putting like this thumbs up sign. Okay, I'm sorry for the bad drawing, but hopefully you can bear with me. Okay, so this is counterclockwise rotation, okay, and this thumb represents your normal from the surface. So basically, if you're going on a counterclockwise rotation, your normal vector always point upwards. Okay, and let's say if you are putting the opposite of that, right, the clockwise rotation, okay, so that means that in this case, if you are, it's supposed to be the other way around, isn't it? Sorry. Okay, it's supposed to be like this. Okay, your thumbs are like this. Okay, so that means that you're going in a clockwise rotation, your normal vector will be pointing downwards. Okay, so that's the idea of the right hand rule actually. Alright, so we're following that principle, we're following that rule to determine the direction of normal vector. It's very important actually, since the normal vector will tie into Stokes theorem later on. We'll see in just shortly. Okay, and yeah, because I mentioned it's below the plane z equals to 4, so therefore our sphere equation x squared plus y squared plus z squared equals 25. Our z is 4, so I substitute 4 inside. Then therefore it becomes 16, right? So 25 minus 16 becomes 9. So x squared plus y squared equals to 9. And this becomes your very familiar circle equation, right? Where x squared plus y squared equals to r squared, right? So that's why your r is 3. Which is basically our boundary curve, basically. Our curve, our interest. Okay? Then Stokes theorem states that basically there's a relationship between the surface integral for the curl of a vector field, okay, which is equivalent to a closed line integral, okay, of the vector field itself. So it's basically a relationship between surface integral and line integral of a vector field. And Green's theorem basically is a special case. Green's theorem is basically when boundary curve. Okay, the boundary curve lies in xy plane. Okay, but basically it's a closed line integral. The whole idea is that it's a closed line integral. Okay, so that's the Stokes theorem, basically relationship between surface integral and line integral. Okay, where it's a closed line integral itself. Okay, so that's the relationship, and you can actually use any of them to solve the problem. You can either go for the surface integral approach or the line integral approach as well. Alright, which we have covered in week 13 of the tutorial, and line integral in week 12. So you can refer to those tutorial notes if you want to recall. If I'm not mistaken, I think I proceeded with the line integral method. Okay, and why I proceed the line integral method is because I found it to be easier. I guess, yeah, I found it to be easier, and I tried to use Green's theorem, even though they said inline has to lie on the xy plane. But Green's theorem will also work fine here, because the thing is that I sort of projected this what do you call it, this boundary curve. Okay, I sort of projected it along the xy plane actually, which is completely fine. You can also do it like that as well. There's nothing wrong. You can project it along the xy plane as well, because the thing is, the plane z equals to 4 and z equals to 0, right? It wouldn't change so much. Okay, so yeah, my force field is basically negative y, x, and 4 because z equals to 4. Then my dr, which is basically just dx, dy, and d0. dz is 0 because at the boundary curve the z does not change, right? Because it's only 4, right? It's a constant. So if you do the dot product between f and dr, this is what you end up having, right? Which is just negative y dx plus x dy. And again, you can use Green's theorem, right? And I initially took the counterclockwise case because typically the formula for Green's theorem is that it's a counterclockwise, right? Clockwise basically is negative of counterclockwise. Okay, so this is, if negative, that means it's clockwise, which we will obviously put later on. Then it just simply becomes 2 dx dy. Now the thing is, the boundary curve here, okay, is a simple circle, right? It's a simple circle, right? As highlighted. Let me just highlight it again in different color. So it's basically a simple circle, right? And the equation is right here. So that's why I opted for polar coordinates, right? So basically, double integral becomes a simple polar integral, right? R dr d theta. Alright, the limits are 2 pi and 0 because it's a full circle, and for r is between 3 and 0 because the radius was, maximum radius we got was r is 3, right? So from r0 to r3 you're able to get the circle, right? So as we do the integration, eventually upon the integration we get 18 pi. But remember that our normal vector was pointing where? It was pointing downwards, right? Because it says outwards, right? Okay, below the plane. So that means to say that our rotation is going clockwise, and we assume initially the Green's theorem is going counterclockwise, right? So therefore for clockwise it's just negative, and this is your final answer, okay, for part 1. So yeah, you can also use surface integral if you, let's say, you're wondering how do I proceed with surface integral. So first thing you do is to try and find the curl of this vector field. Okay, you can find the curl of the vector field, and then our normal vector, since it's going outwards, is just simply negative. Okay, you do the dot product for the normal vector and the force, the curl of the vector field, and then you integrate respect to the boundary curve also, right, which is a simple circle, and you also get the same answer as well. Okay, you end up having the same answer, negative 18 pi. Okay, going on to the second question. So the second question asks us to use Stokes theorem to evaluate the curl, alright, where they given us the force field also. and S is basically the part of this. So if I'm not mistaken, I think this is a parabola. This is a parabola equation. Above the Z equals to 1. So basically starting from the Z equals to 1 plane, assume that S is oriented upwards. Okay. So S means the normal vector. When they say assume it's oriented upwards, they're actually referring to the normal vector orientation. Basically the orientation of N, which I've just sketched by the way. So first we sketch. Okay. So after we sketch, so basically our Z equals to 1. We rearrange the equation. So our surface is x squared plus y squared equals to 4. So of course it's a simple circle equation, right? It's because x squared plus y squared equals to r squared. So our r is 2 obviously, right? Because 4 square root of 4 is obviously 2, right? So it's a simple circle. And since our n is going upwards, that means our rotation is going to be counterclockwise. Okay, it's going to be counterclockwise. Alright? So recall Stokes Theorem. So Stokes Theorem, you have the surface integral, right, which is basically the curl of the force ds, right, is equivalent to the closed line integral again. And again, special case, if you want to use Green's theorem also you can, but normally it's better to solve the closed line integral I think on its own. So for our case, I proceed with Green's theorem for this one, right? So the force field is already given, okay, and since our z equals to 1 for our case, so I just substitute everything with 1 here, so it becomes 1, the rest is as it is. Then dr is just simply dx dy, and 0 because z equals to 1, so it's a constant. Okay, then you do the dot product between f and dr. This is what you'll end up having, which is just simply 1 dx minus 3xy dy. So our p is 1, right, and our q is 3xy minus 3xy. So eventually once you do perform Green's theorem, so this is what we end up having. Okay, this is basically our expression, which is just basically a double integral negative 3y dx dy. Then of course we put in the values, right? We put in the boundaries. Okay, we change this dx dy to r dr d theta. Okay, and of course we change the polar coordinates, right? So basically our limits are between 0 to 2 pi. Okay, x is 2 cosine theta, y equals to 2 sine theta. So as we do the integration, eventually we do all the steps, we end up having 0. So basically the answer for this question is 0, right? To evaluate this evaluate the problem, we find out 0. You can also do the surface integral as well. Alright, basically you have the force field, and then you have the normal vector. The normal vector in our case is positive k, right? It's going upwards. And then once you do the dot product, then yeah, you just do the double integral with respect to the boundary curve, which is basically this one, right? You do a double integral in polar coordinates, and then you get your final answer, which is supposedly 0. Alright, number 3. Okay, use Stokes theorem to evaluate this integral where you got the force field, and C is basically a triangle with the vertices. Okay, so and they're moving in counterclockwise rotation. Okay, here's the thing. Okay, so when we draw the contour region, basically when you draw the triangle, our triangle is 1 0 0 0 1 0 and 0 0 1. Basically it is a plane. Okay, it's basically a plane, or a plane equation. It's basically a continuous plane. Okay, within the x, y, and z. So you need to guys remember that if they give you 3 vertices of a triangle, actually our surface is a plane. Alright, it's a simple plane, nothing more than that. And when they say counterclockwise orientation, that means our normal vector is perpendicular to the plane and it's going upwards, right? Because once you do counterclockwise using the right hand rule, your normal vector will go upwards, right? So in this case, it's going upwards from the plane surface, pointing upwards. Okay, so what does Stokes theorem say? So Stokes theorem say again the relationship between the surface integral, okay? So this is the surface integral, and this is our closed line integral, right? Okay. So I proceeded with the surface integral actually, because for me I think the surface integral is a little bit easier than going with the closed line integral. Since for closed line integral you have to worry about the lines. Since it's not a simple circle anymore, it's a triangle, right, with three different vertices. So they of course will have three different lines, which is C1, C2, and C3. You have three parts to consider, and this is a troublesome. So instead of going to the hassle, why not you use the surface integral, right? Because we know it's a plane already when you identified the surface, so it's pretty easy for us. So the curl actually of f ds can be rewritten as a surface integral of the curl f times the unit normal vector ds. Okay, so therefore we find the curl of the vector field. If you recall from the earlier tutorials, I think it was tutorial 3 or 4 where we discussed about how to find the curl of a vector field, right? So we've discussed about it actually, and this is what we end up getting. All right, so you see you have I. We basically take the matrix of it, like the determinant of it. So del dy times x becomes 0, obviously, right? Because there's no y component x, and likewise it also becomes 0. And then minus j, okay? So del dx times x becomes 1. Del dz times z square becomes 2z. That's why y minus 2z. And then k is 0 also, right? Because we take from del dx times y square 0, 0. Okay, so you're left with your vector for curl f. Then for the normal vector n, we need to find the surface equation, which is a simple plane. Okay, yeah, because the thing is that we're given a plane equation, so we need to actually find a normal vector which is basically perpendicular to the plane itself. So remember, for a general plane equation, normally write it as ax plus by plus cz equals to 1, where a, b, and c are just the coefficient of the plane itself. Okay, so using the coordinates, we managed to eventually find what is our a, b, and c, right? So it's just simply 1, 1, 1. So the plane equation is simply uh, x plus y plus z equals to 1. So to find the plane equation, okay, we need to find the gradient vector for the surface itself and the magnitude of the gradient vector. So it's basically, of course, the gradient vector for the surface is just del dxi, del dyj, del dzk. Referring to the plane, so del dx is just simply 1, right? Because you differentiate x, you get 1. Differentiate y, you get 1. Differentiate z, you get 1. That's why you're left up with ijk. And the magnitude is just simply, magnitude of this vector is just simply 1 square plus 1 square plus 1 square root becomes square root 3. Okay? So, therefore, your unit normal vector is just 1 over square root 3, 1 over square root 3, 1 over square root 3. So, the curl f dot product with a unit normal vector will give you this result, right? But here's the thing. We're not done yet actually. One thing is that our ds, by the way, can also be represented as the magnitude of the surface vector that we found earlier, which was just square root 3, right? So it's just simply square root 3, okay, times the dA, okay? And if let's say that's actually how you can represent ds, otherwise also what you can do is that our curl f ds, we can also rewrite it as curl of f, if you know the actual normal vector, which is just simply n times dA. Straight away you can do it like that, okay? So you don't have to convert the ds into the unit normal vector dA as well. You can also do it like that, and you should get the same exact answer, right? So actually this normal vector, we can also derive it straight to be just basically the just basically the gradient of the surface itself. That's the normal vector. You don't have to really find the unit normal vector and go through all the hassle. Just simplify the gradient of the surface vector, and then you just have dA, which is basically the uh based on the contour, based on the contour, okay, that you want to how do I say, you want it to project, okay, which in our case we want to project this shaded one, this red area is our contour, okay, our contour, okay. So as we do this, right, I also rearrange our plane equation a little bit. So this is our interest, right, negative x plus 1, okay. So I got rid of the I of course found the the magnitude of the gradient vector, okay, times dA, right, to replace it. So this becomes dy dx or dx dy, and square root 3 and square root 3, of course we cancel out, becomes 1, okay. And then we set our limits. So I set up the limits as dy dx. So our y is actually between 0 and this line equation, which is just equals to y equals to negative x plus 1. This is our contour, okay? And our limits for x is between 0 to 1. So 0 to 1, okay? So as we do the integration, step by step, so of course we integrate respect to y first, alright, and then we get this expression in terms of x, and then which just ends up being a quadratic expression. We simplify it, eventually it simplifies to x squared minus x, and then we integrate it, it becomes x cubed over 3 minus x squared over 2, 1 0, so it becomes negative 1 over 6, which is your final answer. Alright, for now we're going to question 4. Alright, question 4, they ask us to verify, okay, if the question asks about verifying Stokes Theorem, what does it mean? It means they want to check that once we write our Stokes Theorem, both the left hand side and the right hand side will give you the same answer, okay. So you need to actually calculate for left hand side and right hand side, and our force field F is already given to us. They given us the ellipse equation also. Basically the ellipse equation is already given to us. 4x squared plus y squared is less than or equals to 4, z equals to 0, okay. So this is our ellipse equation, and we need to find or verify with Stokes Theorem, okay. So first things first, we need to, I use the right hand side. So right hand side I use first. You can go to the left hand side, it's completely fine, but I chose the right hand side first. So we have our force field, right? X squared times 2x plus z squared. For ellipse, okay, this is our ellipse equation they've given to us already, which is just 4x squared plus y squared equals to 4. But we simplified it to this form, okay, which is basically the form of x over a squared plus x squared over a squared, y squared over b squared equals to 1. So I wrote it in this particular form, okay. I divide by 4, so that's why it becomes x squared over y squared over 4 and 1. So 4 I expressed it as 2 squared, right? 2 squared, and 1 is just 1 squared, no problem. We have 1, and I parameterize the x and y into x is cosine t, y equals to 2 sine t. Okay, so I parameterized x and y in respect to t, and our t is between 0 to 2 pi. This is from the line integral tutorial, week 12. So yeah, you can refer to it. Actually, they have the list of ways to convert shapes like ellipses, circles, or other common parts into parameters, right? Expressed in terms of t, because it becomes a simple integral, a single line integral becomes easy, right? So our r is based on the parameters themselves, right? So cosine t, 2 sine t, and 0. So of course when you do the differentiation with respect to t, this is what we end up having, okay. So this one you have to recap from your line integral chapter, and then we do the dot product of the f and the r. So eventually we'll end up having the answer right away, right? So it's 4 cosine squared t, cos squared t, and sine squared t. So we set up the integral. It's a single integral, right? We don't have to integrate any two variables. Just will integrate respect to t. So we got 4 cos squared t minus cos squared t sine t. So I suggest to separate the integrals, because if you separate it, it'll be easier for you to integrate both of the functions, right? So for this one, we can integrate using the double angle, right? Where cosine squared t is 1 plus cosine 2t times over 2, okay? And for this one, sine t cosine squared t, I suggest using u substitution, okay? Where if you say that u is cosine of t, then du dt is negative sine t, right? So you take the negative to the other side, negative du sine t dt. But when you do u substitution, don't forget to change your limits, yeah, because you are substituting your parameter with another parameter. So it's very essential to change the limits, okay? And this one, in this case, we're just using double angle, so we're just simply making it converting a very difficult form to integrate to something far easier and simpler. So therefore, you can easily integrate, okay? And then we got this form, right? 2 plus 2 cosine t, because we had the 4, right? So 4 times half would obviously give us this 2 and 2. Easy to integrate straight away, and we can easily get our answer, right? But for this one, as we substituted our values, right? We got u squared negative u squared du, but our limits were 1 and 1. So of course, if you have the same limits, your answer will be 0, right? So therefore, this integral gets eliminated. It leaves us with this one only, and eventually we get 4 pi. Okay, that's from the right hand side. Now, if we proceed with the right hand side using if we proceed with the surface integral earlier on the left hand side, because the right hand side already is done, now we need to proceed with this one. So then let's proceed with the left hand side. First things first, we find the curl of the force field F, which is just simply 0, 0, 2. Then our ds, okay, which is the unit normal vector times ds itself, 0, 0, 1. Okay, it's pointing upwards also, that's why I chose my unit normal vector with 0, 0, 1 actually, in this case. And this is also a normal vector also. You can say that your actual normal vector is also 0, 0, 1. Okay? You don't have to find a unit normal vector at all. Alright? So your curl is just simply equals to 2. 2 ds. So, of course, you can rewrite it in this equation. And the reason why I wrote it dA is because remember that our normal vector is just simply 0, 0, 1. Okay? That's your actual normal vector. Okay, so your ellipse equation is 4x squared plus y squared equals to 4. So what I did here actually is that because I converted my dA in terms of dx dy. Okay, I think dx dy or dy dx. Sorry, dy dx. Yes, I converted in terms of dy dx. Okay. So I of course set the limits of our ellipse, because once you do square root, so you rearrange it, you get y squared equals to 4 minus 4x squared. So y is between plus minus square root 4 minus 4x squared. So my limits of y are between the negative square root 4 minus 4x squared and positive square root. Whereas my x is between negative 1 and 1. How do I know my x is between negative 1 and 1? Well, because from the equation, if you look into it very carefully, y squared depends on 4 minus 4x squared. So if my x was 1, okay, that means my y is 0, which is confirmed. If my x was negative 1, also the same thing, my y also become 0, right, which is already confirmed. That's why we know our limits of x in between negative 1 and 1. Okay, so after I set the limits, right, we integrating with respect to dy dx. So first I chose dy. So because here is negative and here is positive, so it just simply becomes 2 square root 4 minus 4x squared minus negative 2 square root 4 minus 4x squared. Okay, so you end up having 4 square root 4 minus 4x squared. Okay, so once you have that, okay, then what I did was that I took out the 4, so it becomes 4 over 1 minus x squared, right? And of course, then when you square root it, it simply would become square root 4 times square root 1 minus x squared. Okay, square root 4 is clearly 2, so 2 times 4 gets you 8. And then you have this part which you can use trigonometric substitution. Okay, you can use trig substitution where I chose my x to obviously be sine theta, right? This one you can refer to your tutorial 8 actually. So this one you can refer to tutorial 8. Alright, so you can look back to tutorial 8. So your dx is just cosine theta d theta. So I substituted in first without changing the limits first because I wanted to get the direct antiderivative first of all. So once I did so, okay, we have of course cosine squared theta, which I use double angle identity to make my life easier for integration. Then of course I integrated, I got the antiderivative back. So back to the original integral, I didn't change the theta back to x, by the way. I just put the antiderivative as it is, and I changed the limits. Okay, initially the limits were between the limits were between 1 and negative 1. Yes, so therefore in this case theta would be equivalent to sine inverse of x, right? So of course if sine inverse is 1, you get pi over 2, right? And if sine inverse is negative 1, you get negative pi over 2 or 3 pi over 2. It doesn't matter which one is it. Both of them will give you the same output. Okay? But I chose negative pi over 2 because, you know, it's smaller. So then once you plug in the limits, you end up getting 4 pi. Okay? So that was your final answer. So it's verified. Okay? It's verified because the left hand side equals to the right hand side. Now moving on with question 5, also very same question as question 4. Also we need to verify Stokes Theorem, and they give us the force field, and they give us the paraboloid also, and the circle, okay, as its boundary. So the circle is the boundary. So first we sketch the region. So we have the boundary x squared plus y squared equals to 1. This is our paraboloid, which is just simply z equals to x squared plus y squared. It's very similar to our circle equation, right? Our boundary equation, because x squared plus y squared equals to 1, meaning to say that our z is equals to 1. Okay? In this case. And for Stokes Theorem, remember we have the left hand side, which is the surface integral. Right hand side is the closed line integral. So let's choose the right hand side first. I decided to do the right hand side first. So we have the force field equation, which is already given to us. So we're having our force field equation, and we already have our boundary curve, which is a circle. So by having a boundary curve as a circle, we use the parameters, right? X is cosine t, y is sine t, our z equals to 1, our t is ranging between 0 to 2 pi. Okay? And this one you can refer to basically your tutorial 12 or your week 12 line integral, where they already mentioned like how we can parameterize the curves. So our r is just cosine t, sine t, and 1. dr is negative sine t, cosine t, and 0, right? After we differentiate with respect to t. Okay? So once we differentiate, we do the dot product, and this is what we end up getting. Okay? So of course initially you get y squared sine t negative minus x cosine t. But remember we parameterize our y and x, so don't forget to put our parameters in. Alright, as you put our parameters in, this is what we end up getting, okay, in terms of t. And then we do the integration, right? And I separated the integral in 3 parts: negative sine t cosine squared t, and negative cosine squared t. The limits are between 2 pi and 0 because we already defined our limits for t to between 0 to 2 pi. Okay, so as we define our limits, so we get cosine t, right? Integrate negative sine t and cosine t, but cosine t is 0 for 2 pi and 0, right? Because they give the same answer, which is 1. So 1 minus 1 is 0. Then for this one, sine t cosine squared t, you do use substitution again, And just like before, you will end up having the same limits, right? Once you do the U substitution, it is so 0, so therefore this part is neglected. So the last part is this one. And this part, you have cosine square 2t. So you basically use the double angle rule. Okay? So you leave the half to the other side, becomes a constant. You do the integration. And then you found out you end up having negative pi plus 0, which your answer is negative pi. Okay, that's for the right hand side. Now you do the left hand side, which is basically the surface integral with the curl. So you find the curl first of f, which is 0, 0, and negative 1 minus 2y. And since we are finding the gradient of surface vector, which is our normal vector, by the way, it's our normal vector. So in this case, that's basically our gradient vector of the surface itself. Our surface is a parabola, which is true, yeah. So that's why basically it's just z equals to x square plus y. Z equals to x square plus y square, right? So that means to say that our it becomes what, negative x square minus y square plus z equals to 0. So actually it's supposed to be negative 2x minus 2y here by mistake plus k, right? And then we get negative 2x, negative 2y, and 1. But for the curl of f, when you do the dot product of s, negative 2x, negative 2y gets forgotten, so it becomes negative 1 minus 2y. Okay? So in this case, we use the polar coordinates, right, to do the integration. We use the polar coordinates for the boundary area. Because why we use polar coordinates is because the thing is, as we see from our region, it's actually a circle, right? So therefore it's very advisable to use polar coordinates. Okay, so we must use polar coordinates. All right. Okay, so we use polar coordinates. So of course x equals to cosine theta, y equals to sine theta, I equals to 1. All this from the equation x squared plus y squared is 1. Then we put the limits, yeah, because our theta is between 0 to 2 pi. Don't forget that, very important. Then 1 and 0, you do the integration. So as we do the integration, right, we do integration with respect to r. Okay, which just give us half, is a constant, you can take it out. And then you do the integration with respect to theta, which is of course negative theta minus 2, negative cosine theta. You put 2 pi at 0, and eventually you solve it, you get negative pi. So it's already verified. That means that both the left hand side and right hand side give you the same answer. Okay, now question 6 asks us to use the Stokes theorem to calculate for this. Okay, they give you the force field. S is given to be part of the ellipsoid. This x is not correct, whether it's x squared plus y squared plus 3z squared equals to 1 below the xy plane, and n is the lower normal. Okay, when you say the word lower normal, okay, so of course don't forget to mention Stokes theorem, right? Left side is the surface integral and right hand side is the closed line integral. Okay, and then you sketch the surface as an ellipsoid. So basically it looks something like a tablet, maybe like the medicine tablets that you guys are familiar with. So that's what an ellipsoid would look like. Okay, and basically they're interested in the xy plane only. They meaning to say that your z is 0. Okay, so it's a circle. Technically it's a circle, right? In this case it's a circle. When z is 0, it's a circle, and your n is going downwards because they specifically say lower normal. So now you know your normal vector is going downwards. That means your circle is going in a clockwise pattern. Okay, your circle is going in a clockwise direction. So now in this case, you can either use the left hand side or the right hand side, whichever feels comfortable to you. I think I probably use the right hand side if I'm not mistaken. So yeah, I think I stick with the right hand side anyway. Okay, because the path taken by the contour of the circle we mentioned earlier was clockwise. So yeah, basically z equals 0, x squared plus y squared equals to 1. Okay, alright. So my f force field is just x squared, x cubed, and cos x z. and then of course I know that z equals to 0, so therefore this is your force field vector 0 x cubed and 1, and my dr is simply dx dy dz is 0 because z is equals to 0. So when I do my dot product f and dr, I get x cubed dy. So basically I stuck to Green's theorem actually, because it's in the case where our z is 0. Okay, the contour lies on the xy plane, right? Because it lies on the xy plane, so we can go for Green's theorem. Okay, Green's theorem. Alright, so by using Green's theorem, okay, recall how the Green's theorem general formula looks like, but this is for the counterclockwise case. Okay, clockwise is just negative, so we end up having 3x squared dx dy, and because we are expressing in terms of dx and dy, right? So I had to rearrange my circle equation. I had to rearrange it like this, of x in terms of y, okay, plus minus. So my limits for y in this case, my limits for x actually, are square root 1 minus y squared negative square root 1 minus y squared. For dy, it's just between 1 and negative 1 because my circle is going from 1 and negative 1. Okay, so of course, first things first, we integrate respect to x, it becomes x cubed only, right? Because 3x squared becomes 3x cubed over 3, you just cancel out, becomes 1. Alright, you substitute in, so it just simply becomes square root 1 minus y squared cube minus negative square root 1 minus y squared, the whole thing is cubed. So when you cube a negative number, it becomes negative, right? So therefore it simply becomes 2 1 minus y squared, don't forget the whole square root cube. Okay, and I said to use trigonometric substitution because it will actually simplify the integral a lot more easier, right? So therefore y equals sine theta, theta is sine inverse y, right? So dy is just cosine theta d theta. Okay, then don't forget to change your limits because we are using trigonometric substitution. So 1 and negative 1, right? We end up getting 1 over 2 pi negative 1 over 2 pi. So we, of course, substituted, right? In this case, we end up having what? We end up having, we end up having cosine cube because cos square square root becomes cosine theta cube, cosine cube theta times cosine theta, cosine to the power 4 theta. Oh, okay. So you cannot integrate this directly, okay? So I split cosine 4 to the power 4 theta to cos square theta and cos square theta. And we know that cos square theta would give us a double angle identity, right? Which is just 1 minus cosine 2 theta over 2. So you multiply these two together, okay? After you multiply these two together, you get, you basically get 2 times 2 over 4, 1 minus cosine 2 theta, 1 minus cosine 2 theta, okay? So of course 2 over 4 gives you 1 over 2, which you can leave it there. And this one, basically you just multiply on the terms, so 1 times 1, 1 times cosine 2 theta, and so on and so forth. Once you expand the function, you end up getting this expression. And now you have cosine squared 2 theta. So cosine squared 2 theta, you use a double angle rule will apply. So cosine squared 2 theta is just 1 minus cosine 4 theta over 2. I just based it from the initial formula, right? But instead of theta becomes 2 theta, here becomes 4 theta. So that's the beauty of double angle actually. You can actually apply it for other cases, right? In this case, we cosine 4 theta to 2. Then we integrate, we simplified the expression a little bit, and then we were able to integrate it. And once we integrate it, we found the antiderivative, so it just simply becomes 3 over 8 pi for if you use this limit, and negative 3 over 8 pi if you use this limit. So of course subtract becomes plus, and eventually we're left with 3 over 4 pi. But we're not done yet because our contour is going clockwise, so it's just negative. So don't forget the negative sign. This is your final answer. Okay, so moving on with question 7. So question 7 asks us to use Stokes Theorem to evaluate the line integral where f is given as a vector field. So this is the vector field given in terms of ijk. Okay, and C is the curve of intersection at the cylinder and the plane itself. And C is oriented in a counterclockwise direction when viewed from above. So we are using the Stokes Theorem. Remember, left hand side is the surface integral, right hand side is the line integral. So of course, which one is easier to use, we determine by sketching the surface. So we can see that we have a cylinder and we have a plane, because they clearly mentioned to us that we have a cylinder and we have a plane. Okay, where did it mention? Cylinders already mentioned to us, and they've already given us the plane. So C is the curve of intersection. Okay, so C is the curve of intersection. So what happens when you have a plane that cuts through a cylinder, right? Especially this orientation, if a plane cuts through a cylinder, think of it like you're cutting, like for example, you're cutting a sausage, for example, okay? And you cut it in this angle, what happens is that your sausage, right, or any cylindrical object will have an ellipse. Okay, you'll have an ellipse. So this is what we call an ellipse, right? This is your curve of intersection. And your ellipse, the normal vector, is gonna be perpendicular to the ellipse, right? That means normal vector will be going here. And this is also the same as the normal vector at the plane. Okay, so the thing is that for ellipse, you might need to remember the ellipse equation, and this might be a bit tricky. So that's why I don't choose to go with the right hand side, because if you need to go the right hand side, you need to find the equation of the contour. Means to say that you need to find the equation of your ellipse. So that's why I prefer going with the left hand side, because it's far easier actually, as you'll see in a bit. Right, so first of all, we find the curl of the force field F. It's actually pretty simple, because for I we have del y, we have this. Okay, so this is del dy, just 4, is just 4 only. Okay, del dz for this is 0, so straight up is just 4. The same you can do for j and k also. Eventually your curl is just 4 2 4. It's a very simple scalar vector. I mean, just scalar vector, it's the wrong word to say, but it's like your components for I, j and k are all numbers, simple numbers, just 4 2 4, right? No expressions. And then the normal vector lies on the plane z equals to 2x plus 4y, which I just mentioned earlier. So of course you reconstruct the plane equation. Okay, you bring the z to the other side, and then you find a normal vector. The normal vector actually is basically the, as we discussed earlier, is just basically the gradient vector of the surface, right? So you find the del dx for this expression, which is obviously going to be 2, and then del dy is going to be 4, del dz is going to be -1. So that's why you get 2 4 -1, and once you do the dot product, you end up getting 12. Okay, because 4 times 2 2 times 4 is 16, and then of course 16 minus 4 is 12. Okay, right? Then you get 12 dA. Now dA here, what is it referred to is the circle base of the cylinder is projected into the plane, because the thing is, our ellipse, okay, our ellipse is actually the final surface. Okay, the main projection is actually the circle. Okay, the circular base. I think I use a different color. I think it's having a hard time to see this one. Let me use green color. Okay, okay. Oh, this is too light. You can't see clearly. Let me use darker green. Okay, great. So basically the circle will be projected up to the ellipse already. Okay, so we need to find the contour of the circle itself. We're more interested in the contour of the circle. Alright, the ellipse contour is what we're not interested in, because the ellipse is basically the surface that we projected up to, if you use the right hand side, I mean the left hand side, sorry. So in this case, our circular base is x squared plus y squared is 16, right? Because that's based from the cylinder equation earlier. Okay, so from there, okay, so -4 4 4 -4, we use polar coordinates. So x is 4 cosine theta, right? Y is 4 sine theta, r is 4, and then from there we change the limits, right? dA becomes r dr d theta, and we integrate it. Very straightforward. So we get 8 right after we integrate respect to r. Then we integrate respect to theta. We just simply add theta in it. And then we get 12 times 16 pi. Your answer is 192 pi. Okay? So that's your answer actually. Going to question number 8 also. They ask us to evaluate the line integral of this force field vector over the curve C in the intersection with the cylinder and with the plane. So it's exactly very similar to question 7 actually, because when you have the plane and cylinder they intersect, the resulting surface that comes out is an ellipse, right? And they didn't mention actually whether the surface is moving clockwise or counterclockwise. If they didn't mention to whether it's going clockwise or counterclockwise, it's safe to assume this one. Always assume this case, okay? It's best to assume counterclockwise, okay? Always assume counterclockwise. If they specifically mention uh, the direction of the normal vector, if it's, let's say for example, going downwards, then we already know it's clockwise. If it's going upwards, we already know it's counterclockwise. They mention the direction of normal vector, then we already know the direction, whether it's going clockwise or counterclockwise. If they didn't mention anything whatsoever, then just assume counterclockwise, which I did here actually in this example. So it's very similar. Of course I choose the left hand side because I felt it would be easier actually to tackle the left hand side than this right hand side, right? Because you have to worry about the ellipse. So first step, obviously find the curl. You find the curl, you get 1, 0, negative x. No, not a problem at all. The normal vector, okay? Again, the normal vector basically is the gradient vector of the surface. Our surface is a simple plane only. So it just simply becomes 1, 0, and 1, right? Because there's no y, right? So therefore del dy becomes 0. X is just 1. Z also is just 1. Very simple. Okay? We find the dot product. It's very simple. 1 minus x. Okay? So once we find it 1 minus x, now we're trying to project the circular region of the plane just like what question 7 also. Our x squared plus y squared equals to 9. We're using the polar coordinates. So x is 3 cosine theta, y is 3 sine theta, r is 3, and theta is between 0 to 2 pi. So once we put in the limits, okay, r dr d theta, okay, you replace with dA, just now remember. And then we do the integration with respect to r. So as we do the integration with respect to r, we got a constant 9 over 2. Okay, put it away. Integrate with respect to theta. You get theta and 3 sine theta. So you get here 2 pi times 9 over 2. So your answer becomes 9 pi. Okay, so that's for question 8. Then coming to the last question of the day, question number 9. So also evaluate the integral. Okay, this is a surface integral, right? Where they give you the f, and s is basically part of the sphere. They give you the sphere equation that lies inside the cylinder above the xy plane. So first we consider Stokes Theorem. So we got the left hand side and the right hand side. Okay, left hand side surface integral, right hand side is the line integral. Then we sketch the surface. Okay, so the question said specifically that S, the surface, is basically a part of the sphere and the cylinder. Okay, but they mentioned that it's inside the cylinder, lies inside the cylinder. Very important. So we need to say that the sphere is not on top of the cylinder, it's inside the cylinder. Okay, it's like sort of below the cylinder. So the cylinder is the one that's on the top. Okay, so the sphere is on the bottom. Okay, because it's already stated explicitly. And our surface in question is basically a circular surface, right? Our surface in question is a circular surface. And did they mention anything else? Above the xy plane. Okay, so above the xy plane. So if we say above the xy plane, meaning to say that our normal vector is going upwards. Okay, so I chose the left hand side because I feel that will be easier. So I take the force field vector, yz, xz, or xy. I do the curl. Interestingly, once I did the curl, I found out to be 0. Okay, you can check why is it 0, because for example, if you take the I component, right, del dy xy is just simply x, del dz of xz is simply x, so x minus x obviously gives you 0. And j also same thing, del dx of xy is y del dz yz is y, so y minus y is 0. And for k, is del dx times x is z. Here del dy becomes z, so 0. So your curl is 0. Okay, so if your curl is 0, what does it mean? That means that this whole integral becomes 0. So when you integrate 0, what's your answer? It's just 0. Okay, it just becomes 0 at the end of the day. So therefore, there is, therefore when you evaluate this, it becomes 0. Alright, and if you were to use the right hand side also, you'll also end up getting 0 as well eventually. Alright, so yeah, so that's about it. Now the big question you might be having is that, okay, which one to use? Do we use the left hand side or the right hand side? And I'll say it depends on the context actually, which is easier. Because some questions, okay, some questions, maybe using the right hand side, maybe using the line integral might not be a bad idea. Maybe it might not be a bad idea compared to using the surface, because the surface might seem tedious. But for example, question 8, question 7, where your contour is an ellipse, right? Your path is an ellipse, right? So it's gonna be a little bit tricky. Therefore, I advise using the surface integral, the left hand side, because you don't have to worry about the ellipse at all. It's already taken into account. Okay? And maybe for some questions, like for example, let's see. Like, okay, questions like 6, for example, if let's say your region or your surface of interest is a circle, okay, basically the circle, then you can take this as your contour, and you can use the right hand side also to do the integration using Green's theorem. Okay, Green's theorem if the surface lies on the xy plane. Okay, if it's lying on the xy plane, then you can use Green's theorem, or you can just use the general line integral formula for closed paths. Okay, so I would say it really depends. And some cases you have to use both because the question specifies verify. If the question mentions the word to verify, that means you have no choice. You have to actually use both the left hand side and the right hand side. You have to actually do both. You cannot just skip. Okay, so yeah, it really depends which one feels easiest to you actually. That's why I don't like force you guys to choose the left hand side or the right hand side. It really depends on how you feel, which is the easiest method for you. Sometimes one is easier than the other. Sometimes uh you know, that one you chose might not be easy. For example, this one, right? This one right away. Okay, for this kind of question, you might think, oh, maybe I might go for the right one, Stokes Theorem. But I would not advise it because you'll have to worry about 3 parts, C1, C2, C3. So it seems very tedious. To save time, why not go for the left hand side, right? So it's all again a choice thing. It's all really based on choice. Which one is better? Whether you want to go for the left or the right hand side, it's really up to you. And if the question specifically said verify, then yeah, you'll have to actually verify. Okay? So we've already reached the end of the tutorial already. So that's about it. And again, thanks for watching. Okay? And all the best for your final exams.